Hello, welcome to today's COP30 webinar, A Guide to Alignment in the Built Environment, which we're thrilled to be sharing with you after close to 2 insightful years of collaboration. I'm Rama Danaevich, Autodesk Global Impact Partnership Lead and Liaison Delegate to the World Business Council for Sustainable Development, the WBCSD, under whose auspices this work took place. Next slide. I thought it would be helpful to share the agenda for the session. I'll give you an overview of the project, set the stage, provide context for the work, and then hand you over to my wonderful colleague, Marta, to share more specifics about the work and to moderate the panel as we proceed through the presentation into part 2, the findings, aka the most interesting part. With me online today are 12 design and engineering experts who are representing their companies and colleagues who poured countless hours into the work we will be sharing today. These excellent speakers will walk you through the project and the outcomes. I know you're eager to meet them, but first let's give you some context. Finally, at the end of the presentation, Marta will share the summary and recommendations, and then we'll open it up for a short Q&A. You can ask questions in the Q&A. So let's get started with some context setting. Here's one, a scary image of the damages of climate change. It's always hard to choose which image to put here, which global disaster to point out to make the point, and you don't need to hear it again. It's why you're all here. But let's repeat the important statistic. The built environment contributes 42% of global greenhouse gas emissions. As a tech company, we're here during COP30 because all of you use technology and tools to plan, build, and renovate the built environment. And it's crucial for all of us to think about how technology can work to address the reality and reduce carbon emissions. Now to the specifics. Architecture and engineering professions are looking for the most efficient methods to connect BIM models to embodied carbon. Today, we have many tools, data sets, and calculators, which result in many paths. You can give that a click to get to BIM to carbon assessments. However, practitioners really just want an efficient, streamlined path to get from A to B. Click. To explore the many paths that exist in the industry. Which brings us to this project, which we developed, again, as I mentioned, under the auspices of the WBCSD. First, we developed a proof of concept to unpack the various ways that these 6 global architecture and engineering firms approach embodied carbon assessments and measurement. By analyzing the same Revit BIM model and sharing the details of their specific workflows and processes, we discovered opportunity areas for better alignment across the firms. And building on that discovery, we're excited to share our learnings with you and the industry today. I just wanted to give a little context also to the WBCSD to say the World Business Council for Sustainable Development, and I'm sure you'll be hearing them from them many times during COP, has a membership of about 250 people, 250 companies, and those 250 companies represent about 25% of global greenhouse gas emissions, and so the opportunity and to work together with members and non-members to do this project was incredibly important. You've seen the companies involved, but we also wanted to show the people behind the work. As you can guess, this was a massive effort across multiple stakeholders, across multiple geos. And you'll hear firsthand today from a subset of this terrific cohort comprised of some of the leading experts in decarbonization. This level of expertise is exactly what's needed to help collect, synthesize, and extract the data needed to formulate best practices that will help not just those in the cohort, but all of you working in the industry. An immense thank you to the cohort, the executive sponsors, the WBCSD, and my colleagues at Autodesk for making this possible. Next slide. This was a time-consuming effort by the cohort who volunteered their time, so I want to recognize a few benefits to the cohort of their participation. First of all, lots of learnings across the cohort, the ability to build relationships across companies that often compete with each other for business. The participating firms you will hear from today are taking learnings back to their own companies to streamline their own firm practices. Those sharings are made possible because of the neutral environment provided by the WBCSD. And most importantly, let's recognize that no single firm can single-handedly decarbonize the built environment. It's about collective influence. It takes radical collaboration like this project to actively shape best practices that these firms and you can take away with you today into your work and through this collective work, which might one day lead to industry-wide standards. How many of you in the audience attended a panel discussion on the first phase of this project last year at COP29? This is the continuation of that work. You'll hear last year's findings referred to as the proof of concept, or POC, which effectively proved the concept. The work we are presenting today is phase 2, which we go even deeper into BIM workflows to understand workflows and establish guidelines of BIM best practices for transparent carbon assessments toward a North Star goal to standardize embodied carbon assessment processes as an industry. And now I'm going to hand it over to the panelists, practitioners, and my fabulous colleague Marta to get into the details of the project and its outcomes. Over to you, Marta.
Thanks, Rama. So you're going to hear from this amazing group of participants that represent a breadth of expertise. They come from multiple geographies, and as you know, they represent a handful of firms, including Arcadis, Fosters and Partners, SOM, Ramboll, AECOM, and Arup. And with that, I invite them all to quickly introduce themselves.
Thank you, Marta. Hi, everyone. My name is Sandra Petkuta. I'm a solutions consultant at Arcadis, and I'm based in Vancouver, Canada.
Sorry, I was muted. Hello, my name is Margarida Gonçalves. I am a global sustainability impact specialist focusing on the life cycle assessment methodology, and I am based in Portugal. Thank you.
Hello, I'm Chris Trott. I'm a partner at Foster and Partners, where I'm the head of sustainability policy and research. I'm located in London and have been in the centre of our carbon work since the Paris Agreement and COP15. Thank you.
Hi everyone, my name is Rita Swanepoel. I'm a partner at Foster and Partners, and I'm also the head of BIM and Design Systems, and I'm based in London.
Hi everyone, this is Dana Farr. I have a background in architecture and a master's in design and management of sustainable built environments. I work as a BIM and design systems coordinator at Foster and Partners, and I am based in London.
Hi everyone, I'm Leandro Oretti. I'm part of the BIM team in Foster and Partners. I'm an architect and BIM coordinator.
Hi everyone, I'm Andrea Colombo, a civil engineer and structural BIM coordinator at Foster and Partners, based in the headquarters in London.
Hi everyone, I'm Eric Stimmel. I'm an architect and a BIM leader at SOM, where I'm part of the core design technology team, working on firm-wide initiatives like this. I'm based in San Francisco, California, and I'm very happy to be here today.
Hi everyone, I'm Paul Astle. I'm the decarbonisation lead for buildings for Ramboll. I am based in the UK, but my work is across our global portfolio.
Hello everyone, I am Javier Sanchez. I am an architect working as BIM manager within the AECOM Spain's digital team based in Madrid.
Hello everyone, I'm Laura Gomez. I'm an architect and a senior sustainability consultant in AECOM, and I'm based also in Madrid, Spain.
Hello, I'm Jordan Woodson. I'm a structural engineer with Arup, based out of New York.
And I'll wrap up as your moderator today going forward. My name is Marta Bouchard. I lead a sustainability solutions team in Autodesk, and what a cohort. Just want to acknowledge the global presence that we have here today, and it's just really incredible. So let's jump into the work. In order to achieve the outcomes we're about to share, we did need to ground our work in real models and real workflows. So we decided to use the Revit sample model called Snowden Towers for several reasons, which you can see here. Although we selected a Revit model, our findings can absolutely be applied to any BIM software. We also needed to align on a reporting framework structure. And for this, we used the Royal Institute of Chartered Surveyors, or RICS, Whole Life Carbon Guidance to structure the carbon assessments you're about to see. This provides a real industry use case for the carbon data being extracted and assessed by this group. And just like with the BIM modeling tools, our findings are actually agnostic to any specific reporting framework and could be applied to any reporting structure. So we get into the fun part. What did the results of our efforts find? Here's a quick recap from the initial proof of concept. So we're going back in time about a year and a half. So as a summary, we see each of the cohort's firms represented as a single approach on this view, where the y-axis is a measurement of embodied carbon for, in fact, just the structural scope. So I want to be clear, this is not a whole building. It was structural systems which were selected as high impact carbon scope. Each of the bars here corresponds to the RICS categorization of reporting data. And we have 7 approaches because one firm actually applied 2 different approaches to the data, resulting in slight variations even within a single firm. Now, what we found is a 34% variation across the results. So if you zoom out from this, you can imagine how this has a huge implication for carbon regulations that rely on benchmarks, carbon intensities, and corporate commitments to net zero, which rely on offsets or other things for carbon impact factors. Now, what you see here on this slide is last year's resulted work, where we have 6 key areas of discovery explaining why we saw such divergence across the 7 approaches. We identified key elements of an embodied carbon assessment process, the fact that the data structure maps from BIM software to a reporting framework, variation in identifying the spatial boundary of what is even assessed, how a model can be post-processed and then fed into material takeoffs, that there are assumptions made around non-modeled elements, and lastly, there are different approaches to selecting embodied carbon factors. So this was the baseline of all of our learnings. You can read this report, the first report, for details, but this is critical. It serves as our jumping off point for phase 2, which you're about to hear about. We are going to go deep into the how. We went back, we interrogated our work and understand what caused that 34%, and we want to better understand our processes and workflows so that we can seek alignment across our firms and design best practices. With that, we're going to jump right in. What can we do to reduce the variation? Welcome to phase 2. We're taking those learnings from phase 1 and moving into phase 2, which goes deeper into the disparities and in finer detail so that we can get recommendations and guidelines for you all. We are going to hone into the actual step of translating BIM into quantities, but I want to make sure you understand we are excluding the application of carbon factors. So that was a variable that remains in this work because it's a very big topic that we can address another day. In the future, we'll also be starting a phase 3, which will explore embodied carbon processes in the construction phase with those professionals. But here we're talking about phase 2, and we're going to walk away today with some design guidelines. So kicking us off, we are going to talk about the why in this variation, and we interrogated the root causes for the variation I just presented. And we're going to introduce guidelines for how practitioners can get started in BIM on the right foot and with the end in mind. Today, we've structured our findings into 6 categories of recommendations, and if you listen very carefully, you'll actually note that while we tried to create clean categories, not everything fits neatly into each bucket, and there's going to be some overlap and recurring themes. And while everyone collaborated across all themes, each firm is presenting to one of them today. We'll be handing off, and I will be teeing up each section according to these 6 as your moderator today. Starting with the first section, preparation for carbon assessment. What can we do at the beginning to prepare for a carbon assessment? So in phase 1, we focused on a use case. We looked at carbon phases for scopes A1 to A3 for a fairly detailed model. But if we extrapolate to multiple use cases across many phases of a project, it introduces even more potential for variability. So to get started, here are the guidelines that can help you set your path to prepare for carbon assessments. And I'll hand it over to Sandra.
Thank you, Marta. So we begin this section with a focus on preparation, because how we frame and scope an assessment directly shapes its consistency, transparency, but also its outcomes. So while our cohort teams understood carbon scope really well, we still saw differences in how spatial boundaries were set and how non-modeled elements were handled. So to address this, we structured the process around 3 core pillars. That will be explained in the next slides, but namely, it's about setting the purpose, matching the model, and communicating clearly. And at the end of Arcadis section, we'll provide you with a summary of discussed topics, as well as with a practical checklist for setting up a robust carbon assessment.
Thank you, Sandra. So before starting a carbon assessment, focus on 3 main things. First, the purpose. State the goal and the scope of the assessment, the life cycle stages included, and the data sources. For example, your goal may be to support internal decisions on how to reduce embodied carbon or for compliance purposes. Second, the method and methodology. Decide which standards and guidelines you will follow, such as ISO or RICS, and identify the impact indicators and tools that you will use. Third, data transparency. Well, this topic will be discussed further in this presentation, so very briefly, be clear about where your data comes from and what assumptions you make. In summary, if you are clear on these points before starting your calculations, your carbon assessment will be stronger and will build trust with reviewers and stakeholders. Next, please. In projects, the level of data detailed and the precision of carbon results depend on 2 things, the design stage and the goal of the assessment. At early design stage, the model has limited details, so we rely more on assumptions and benchmark values to estimate material quantities and carbon emissions. Here, our focus should be on the elements with the highest mass and the highest carbon intensities. For a standard building, this usually means concrete, cement, steel, and aluminum. And at this stage, the analysis is mainly for internal decisions like helping develop low-carbon design options. As the design becomes more detailed, we have better data and more granularity. Now, we can use all the available information, such as the full list of materials, or even extract quantities directly from the model. These allow us to move from high-level estimates to detailed carbon assessments. In brief, it's important to start the carbon assessment in the early design stage because these help us to find and implement low-carbon strategies before the key design solutions are made or closed. Next, please. Finally, to make a carbon assessment reliable and robust, there are 2 important steps. First, sensitivity analysis. This means checking out changes in assumptions or input data affect your carbon results. For example, the electricity mix or the amount of recycled content in materials can vary by location or the technical details. So sensitivity analysis is especially important in the early design stage when we often have to make a lot of assumptions. And if we don't test how these assumptions change the results, we may miss opportunities to reduce carbon emissions. Second, the quality assurance. Well, quality assurance is about validating the assessment, making sure the data, methods, assumptions, and results are correct. Even if you don't need a third-party verification, it's important to review the work internally to make sure the results are correct. And finally, remember, there is often more than one correct way to do the carbon assessment, so it's important to have a clear goal and method, transparent assumptions and data, and to understand how key inputs affect your results. This is what makes your carbon assessment reliable and strong. Thank you, and next slide.
Thanks, Margareta. So to wrap up, we wanted to leave you with a little bit more practical checklist for setting up a strong carbon assessment. So first, Define the goal and scope clearly. Ask yourself questions. Are you benchmarking or are you already reporting for compliance? Second, select a reporting framework and make sure your data sources align. Third, match your preparation to the project stage and also model detail. Fourth, prepare your BIM model for data extraction for things like materials, quantities, classifications, and other data that would support your LCA mapping. Fifth, account for non-modeled elements. You might need to use assumptions and even manual entries. Sixth, document those assumptions very clearly, because together these steps will help ensure that your assessments are not only robust, but it's easier to communicate, collaborate, and also improve it over time as needed. And the last 2 points will link closely to the downstream workflows, which the rest of the cohort will speak in the later slides.
Thank you to the Arcadis team for that first section. So we're moving into section 2, which is a topic about how practitioners set up a building information model, or BIM, from the outset to prepare for the assessment. As we identified in phase 1, the data structure of BIM software does not align neatly for any one reporting framework. And so how can the model be established with the end goal in mind? I hand it over to Rita.
Thank you, Marta. In this section, we will cover the process of preparing models for embodied carbon assessment. It is key to highlight why standardizing the model setup is so important. To achieve an optimized and precise carbon assessment, the model must be built on a foundation of reliable geometric information plus consistent and accurate non-geometric information. Standardizing ensures that this information is structured consistently and extracted with the advantage of traceability. This reduces errors, streamlines the workflow, and ultimately enhances the accuracy and reliability of the carbon results. Without standardization, assessments can easily become incomplete, inconsistent, or even misleading.
Next, please. Before we dive into explaining the model setup process, it's important to understand the broader context of the BIM to embodied carbon assessment workflow. It consists of 2 key stages. The first is model setup, which takes place inside of the BIM environment, and the other is post-processing, which occurs outside of the BIM environment, but is highly dependent on the accuracy and quality of the model setup. Now, focusing on model setup, this stage includes data integration supported by an iterative QA/QC process for both geometry and metadata. Once the model is verified, we move into setting up a data export template, preparing information for post-processing. But before integrating any data, it's essential to define the scope of the carbon assessment, as Margarita said. This is typically managed through filters or custom parameters, enabling easier visual inspection and scope clarity. In line with the model element responsibility matrix, any placeholder element from other disciplines can be placed on designated work sets. This allows for better model quality control during early design stages. All integrated data should follow a standardized structure with uniform naming conventions, hierarchical consistency, and complete 3D geometry. This also includes correctly assigning both predefined and custom parameter fields, such as consistent naming of families and types, clearly defined materials, and accurate element buildups. Once scope is confirmed, custom parameters for standardized reporting categories, such as those defined in the RICS framework, should be applied, and this can be visualized through filters. Next, please.
Thank you, Rena. Yes, and the QA/QC framework should be set up and followed regularly to maintain consistency and alignment, covering geometry and information-related checks, such as no duplicates or overlap elements, no placeholder elements, no hidden elements, avoid generic labels, detailed material properties, and define role function. As the data export template, it should be set up as material takeoff and should include the fields needed for carbon assessment, which are twofold: informational parameters, family, type, predefined reporting categories, and dimensional parameters, volume, area, and thickness. Once these steps are complete, the information is ready for extraction. Post-process and carbon calculations are usually done outside the BIM model. So when setting up a BIM for this purpose, it's important to keep the data structure clear and focus on the final output, and to regularly check the model to ensure the data is accurate. Next, please. In conclusion, to achieve and maintain a reliable carbon assessment, two things matter: geometry and data integrity, and that is through consistent geometry, accurate materials and quantities, and consistent data tagging. And this leads to the second important thing, which is the export integrity, where gaps and errors are detected early, data is verifiable and traceable to source, and exported data is validated. Thank you.
The final important matters about the model setup for carbon assessment are the model's federation strategy and the export templates. In the daily practice, one of the main challenges of exporting data from digital models is dealing with large and complex project scenarios, where the federation strategy involves multiple models shared across different disciplines and several stakeholders. Each design branch may also have further breakdown according to the area of the project or its subdiscipline. In the case of the structural engineering field, for example, a common subdivision of the model is according to the macro groups, such as the roof model, the superstructure, and the substructure. Here comes the importance of having a good export template. Ideally, it is a Revit schedule where you collect the important and relevant data that you need for the carbon assessment. As mandatory parameters, we would like to recommend, at least as good practice, the Revit RX categories in order to facilitate the mapping according to the report framework, the materials assigned to each element, and the quantities, in this case the volume, which will be automatically calculated from the software. So, in conclusion, why it is so important to have an efficient export template? Because the main reason it ensures a structured, consistent, aligned dataset, and it is also a good chance to run a final check and make sure all the information provided are correct before the final export.
One large area of discussion that we identified in the first phase of this work was the fact that some elements in the model would appear in multiple discipline deliverables, such as architectural and structural. This creates a gray area of which model to defer to, especially if that's not addressed clearly and transparently across project stakeholders. I'll hand it over to Eric from SOM, who will talk a little bit about exactly why this is tricky.
Right, so it's fairly common for elements to be modeled more than once. So let's just get that out of the way up front. It's going to happen in your project. It could be different disciplines or even within different models from the same discipline. And as Marta mentioned, we found this to be true in the models we use for the POC. Obviously, this is a problem if we intend to use the quantities from the models for things like cost estimating and carbon accounting. Next, so if as you've already heard, the setup of a project is important. It will provide a framework for the team to do things the right way. And one of the things that they need to be prepared to do is deal with overlapping elements. So first, know that this is a common problem. In some cases, as I said, this will be pure duplication of elements, and in other cases, it will be a partial overlapping. Both of these are problematic, and I'll show you a couple of examples in the next slides. But regardless, you need to be aware that this is going to be a problem at some level on your project. It's also important to let the team know that this matters. They're going to be focused on other things, producing drawings, refining the design, updating the program, whatever it is. And if they don't know this is important, it won't be addressed. And then even before you talk with them, even if you talk with the team about doing this and they have every intention of avoiding overlapping, check this before extracting the quantities. And then, of course, be prepared to deal with that when it happens. So next slide. In our sample models for Snowden Towers, there were notable overlaps for walls between architecture and structure and the site model, as you can see in this colored view. In some of these cases, these were exact duplicates that were easily filtered out, but in other cases, like the entrance to the underground parking, these overlapping walls were different thicknesses by 6 inches. So some care has to be taken to use the right walls and to understand if the difference is significant, and it should just be accounted for in a different category. Next. We also found more irregular overlaps for floor elements between the architecture and structural models. These were cases where the intent of the architecture model seemed to be to show the floor finish, but the floors also included the structural slab. So these compound elements have to be discounted as part of a quantity takeoff. And although there weren't overlaps with the site model per se, there were floors in that model. And there was even a floor in the electrical model. We didn't see many of these in this set of models, but non-structural equipment pads and sometimes walls can show up in other discipline models, which is something that needs to be accounted for as well. Next slide. We had overlaps of columns between the architecture and structure model. In many cases, the architectural columns are furring. These were architectural columns are furring around the structural columns, and they both needed to be accounted for, just not as columns. But in other cases, these looked like duplicate elements that should just be excluded from a quantity takeoff. So of course, we want to avoid this issue as much as possible and only have one party model each element. Fortunately, we already have a strategy for this in the form of the model element table. This is an example of the AIA document, but you'll see this in other forms on other projects. We have the same concept. Yeah, we could even take this one step further, and in addition to identifying the model element author, we could identify a carbon data responsibility column. That would help emphasize the importance of this data and allow for these two things, the model element author and the party responsible for the carbon data, to be untethered from each other if needed. So there are plenty of strategies for working through this in the models, and we've seen a couple of simple visualizations using built-in features of Revit. I would strongly encourage visualizing this in the model with filters or something like that. This is what models are good for, but there's also other ways to check for duplicate overlapping geometry, including warnings, interference detection, third-party add-ins. But clearly identifying the responsible party is going to take you a long ways to clarifying this information. So while floors, walls, and columns are particularly notable, other elements could also be double counted if we're not careful. So here's a short list of elements to pay particular attention to. Thank you.
So this group discussed non-modeled elements at length because we know there are several reasons elements may not be digitally modeled, such as the rebar in concrete or the studs in walls. When there is no element representation in a model, that introduces room for interpretation, assumptions, and therefore variation. You're now going to hear from Ramboll to discuss some guidelines for how to address common non-modeled elements.
Thanks, Marta. Yes, so we've heard about what happens when you have more than one element, but now we're going to talk about when they're not modeled at all. So just to define what we mean by non-modeled elements, we're talking about any material or component which is present in the actual construction but hasn't been captured in the model. And there can be a variety of reasons for that. There may not have been enough information at that design stage. It may take too much time and effort to actually capture those elements in the model. It just may not be worth it. Or indeed, it may be already assumed or planned that those things will be captured through a different method. So many different types of reasons and many different types of elements are within this category. So the issues that we have as a result of that is that these elements can account for quite significant quantities of materials. We'll hear a bit more about that in a second. And as a result, they can be overlooked from carbon assessments altogether. It's quite difficult to know what's not there if you're not expecting it, of course. And then when it comes to the actual pitfalls, one of the key issues that has to be addressed is who's responsible for these elements. We just had a great example from Eric there about identifying who's looking after which elements, but we also need to identify who's not modeling those elements, if that makes sense, and how it's going to be captured separately. We also need to look at the functional units that are used, because if it's not going to be captured in the model, it has to be captured somewhere else. It's really important that we use the right units, and those are the consistent units in the way that we capture it separately. And as a result of all these things, there's a big opportunity for risk and for variability in the assumptions between assessments, assessors, and firms. So this is a really important area that we need to get more consistency on across the whole industry. Next. As a few examples here, we're going to focus in on the structures to begin with, just because a lot of the focus in this round was the structural model. So a few classic examples, the main one being reinforcement. It's quite unusual to model reinforcement. In Ramboll, our Norwegian team does model it, but it's quite rare. And so as a result, most people treat reinforcement as a ratio of the concrete. And of course, that invites errors because it depends on what factor you use for that ratio and whether you take into account other factors as well as the units that you use to do that. There's also things like steel to steel connections or steel to wood or indeed steel to concrete connections. They are rarely modeled because of the numerous number of them, as well as the fact that they're quite complicated. So again, this can be an area where they're not captured at all and they're used as a ratio of the steel tonnage quite often. Then there's things like steel decking or proprietary elements. These are sometimes modeled as an indicator in the model just to make sure they're captured, but the thickness of the element may not be there. And in fact, that's what we found in this model. We had the actual element was captured, but it had zero thickness. And so this is a really good example of things which are partly captured, but not fully in a model. And that means that you have risk of misinterpretation that needs to be addressed. A few more examples here as well. So going beyond structures, there's also things that have multiple layers. So for example, if you had a ground floor slab and it might have a membrane and then maybe some insulation, etc., often those things aren't necessarily modeled and they can be lost. There's also a situation where we have things like internal partitions or ceilings, again, that might have multiple layers, or they might have secondary systems to support them, and they often don't get modeled because it's frankly too much effort to model them and there's not enough justification. But it's important that we capture those materials separately. And then there's just things that are very, very complex and just not justifiable to model at scale. So again, all these things we need to be thinking about when we're developing a BIM model and recognize that it's not a perfect model of what's actually built. So when it comes to carbon, we've got to fill in those gaps as required. Next slide, please. So what are the impacts? Well, in this particular example of Snowdon Towers, we worked out that around 5% of the structural mass was in these non-modeled elements. That's the rebar and the connections, etc. But that 5% of mass accounted for 20% of the carbon. So that's a really significant amount of carbon if you're not capturing it properly or indeed consistently. So really important that we pay attention to this. One of the things to be aware of is that it's often the high carbon materials which don't get modeled because they are the sort of connectors between different components. So these are important things. They're high carbon. It may seem like a small mass, but actually it makes a big difference. We also saw a lot of inconsistency in the functional units used and the ratios, etc. So very important to think about all those different things. In terms of what we can do to address this, there's three key areas: transparency, consistency, and collaboration. Transparency is really, really important. We've got to be very clear on what is modeled and what isn't modeled, and really make sure that everyone in the whole team understands that. We've got to be consistent with how we're going to address these non-modeled elements. Is it going to be a factor? Is it going to be something else? How are we going to make sure we have the same units, etc.? And then we need to make sure we really collaborate with every member of the team. The architect, the engineer, the modeler, the designers, the assessors, they all need to understand what role they have in tackling non-modeled elements and make sure we all do it as consistently as possible. Thank you.
So coming to the next section, we did do quite a bit of unpacking, line by line of Excel exports and many discussions. There were several common pitfalls, some that were straightforward and some that took us by surprise. Some were tied to larger scopes of misalignment, and others were as small as precision of the settings in the BIM schedule, something as small as a rounding error or unit conversions. In the next section, AECOM will share some common pitfalls for misalignment and a checklist to avoid these missteps.
Thank you, Marta. In this chapter, we are looking at some key challenges when calculating embodied carbon using BIM models. First, the format of carbon reports heavily influences how BIM data should be structured. Reports often require breakdown by system, material, or life cycle stage, and demand a traceability of assumptions. Then, within the BIM model itself, problems arise if it wasn't properly set up. Low data levels, poor classification, or mismatched categories like modeling a roof as it was a floor can reduce the accuracy of the assessment. Inconsistent units also add complexity and risk. During data extraction, errors like duplicated quantities or counting placeholders can distort the results. Without a clear traceability, it's hard to validate or reproduce the findings. And finally, aligning BIM data with carbon databases is another challenge. Matching quantities to multiple sources often requires heavy post-processing. Even well-structured exports may need rework to link elements with the correct EPDs. Ultimately, the quantities post-processing effort will depend on the type of BIM element. The accuracy varies between elements, and some parts might need more refinement outside the BIM model. Next, please. Think of a concrete slab, or a beam, or a column. When calculating carbon for concrete elements, we usually rely on the volume, which is the most common unit used in carbon databases. If we assume that these elements have been properly modeled, we could easily have a pretty accurate carbon calculation, having only taken into account its geometric properties in a straightforward way. But what if, instead of a simple concrete slab, what we have is a metal deck floor? In most cases, the metal deck isn't properly modeled in BIM. Usually, we just see a basic extrusion of the slab footprint using the maximum thickness across the entire element. As the quantity comparison shows, calculating carbon directly from that model would inflate the results by nearly 30%. This is where post-processing becomes essential to ensure the accuracy of the assessment. Up next, my teammate Laura will share some practical tips or best practices on how to avoid or work around these common pitfalls.
Thank you, Javi. A successful carbon assessment is the result of the cross-collaboration of two key project roles, the BIM specialist and the carbon assessor. And the rest of the stakeholders and team members need also to be aligned so the result is accurate and complete. So in this slide, we can see in a few moments, there we go. So in this slide, we can see that there are a few interconnected factors that need to function precisely to avoid the common pitfalls that were highlighted before. The first one, as already commented in the POC by the cohort, is that the carbon assessor needs to make sure that the priorities and the framework of the assessment is set. Then the BIM specialist can engage with the team and ensure the model is properly set up. It is key to establish clear modern protocols to ensure, for example, consistency in granularity, consistency in units and materials, and uniform naming of elements and layers. One of the critical steps in the process that can be overlooked is the check and validation of the structured data against the model geometry. A visual inspection and cross-checking the structured quantities against the BIM model, is key to identify duplicity of elements or modeling gaps. Next one, please. Another common pitfall is that the reporting categories classification does not normally match directly with the default categories in the BIM environment. So to address this, it is recommended to add additional metadata to the BIM model. For example, in the POC exercise, an extra parameter was added in BIM to map each element to its corresponding risk category. It is also recommended to develop a visual strategy. The goal is to provide an intuitive way to perform quality checks on the data that has been exported. It can be an actual color diagram, like the one we are seeing in the slide, or any other kind of data visualization, like a dashboard, for example. Next one, please. So as a summary, we also wanted to provide you with a quick checklist that includes best practices to avoid these common pitfalls. The first one would be to structure the BIM model to include information down to the individual elements, while filtering out generic items, placeholders, or detail lines. The second point requires setting up in advance the units and the categories in the BIM model to align them to the reporting framework. The third one is paying special attention when calculating the area for carbon standardization. The fourth point would be trying to use local or national carbon databases, just to avoid additional calculations during the post-processing. Another important item is to be aware of the difference in the numeric formatting depending on the region, as not doing so can lead to the misinterpretation of the values. Finally, it is important to acknowledge that the BIM software may have limitations. So when the geometry does not have enough information, it is advisable to enrich it with data. So if we were to highlight one key idea, it would be the importance of letting the specific reporting needs guide how the BIM model is organized, as this will definitely shorten the post-processing, and in doing so, it minimizes the chance of human error. Thank you.
Amazing. Thanks to you both. As we bring this to our last sort of chapter of their findings, you're going to see that so many of the recommendations already have talked about clear communication and transparency among team members and data and documents. But as a cohort, we've come to the conclusion that given the global variation in regulations and software and standards and local practices, that achieving 100% alignment is currently not feasible. However, we can address transparency and granularity so there is flexibility with assessing the results in order to review the findings in an apples-to-apples comparison. For our last section, I'm excited to introduce, to bring over Arup's Jordan Woodson.
Thanks. So if we circle back to the main problem we're trying to solve when we perform a carbon assessment, we're ultimately looking at a bill of materials and multiplying it by associated carbon factors for each of those elements. But the reality is we're sort of in a gray state where the barriers are all fuzzy. What materials do we count? What are the exact carbon factors? What is the scope of the assessment? And assessors have to make strong assumptions to be able to sharpen these boundaries, if you can click, to sort of really set the stage of what they're going to assess and define those limits. If you go to the next slide. And if we start to think about a BIM model is great at quantifying sort of what we've populated in the BIM model for quantities of materials, and we can assign materials in BIM. But there's a lot of data enrichment and refinement that needs to go into a BIM model at the end of the day to let us get to a bill of materials that is appropriate for a carbon assessment. So we might have to account for non-modeled elements. We might have to group the data in BIM in different categorization buckets for RICS or ISO. The materials might be, well defined by volume, but we actually know a carbon assessment factor by the quantity of that unit and the MEP side. So there's a lot of gray zone that has to take a BIM model and actually turn it into that carbon assessment. And in all of that light blue area, assessors are making assumptions that they need to define. Next slide. And if we think about the carbon factor side of the equation, we don't have carbon factors for every material or product we want to use. And so we're sort of in a realm of having to pick what's most appropriate or what's available for what we have. And so that might be reflected by a carbon factor that's a global average. It might be a regional average or an industry average, or we might have the exact product's EPD. But each of these carbon factors that we're picking from has sort of a different distribution of how quote unquote accurate it will be. Some global averages are super, if you can go to the previous slide. Some global averages in this top diagram reflect a tight distribution where a global average would reflect a product-specific EPD really well. Some factors are heavily influenced by region, highlighted in the middle slide. An example of this is steel. Depending on if your country produces steel with a basic oxygen furnace or an electric arc furnace. And the last, we might have products that are all over the map, and you're not really going to get a good definition without a product-specific EPD. Next slide. And then as we progress through the design process of designing a building, our comfort level and accuracy of all of these things varies over that timeline. So if we look at quantities, at SD or REBA stage 2, we might have a pretty good sense of what the quantities are in terms of like an 80% estimate. And that will only go up as the project gets further defined, but we won't know the actual quantities until the end of the project. Carbon factors, as I mentioned, in an ideal scenario highlighted by that darker blue line, we have a pretty good representation of that material through an EPD. And then at the end of the project, we can verify it through what is actually procured on the construction side. But some products don't have EPDs, and then some products at the top of the scale, are super well defined. And then ideally, the scope of the assessment on the right-hand side should be consistent throughout the project. Not only do we want to be assessing carbon apples to apples amongst projects that are different within a project, it's helpful to know how carbon is changing over the design life of the project. So we want to keep that scope consistent, and if we add further detail, we want to be able to pull that detail away so that we can always compare an apples to apples from the beginning of a project to the end of the project. We can jump to the next slide. There's a few click-throughs here. And so let's just go over some quick examples on sort of the power of assumptions. If you go to the next, yep. So a BIM model might tell us that there is a 90 millimeter thick concrete slab over a steel structure that has 30 kilograms of steel per meter squared. If you click, and so an assessor may say, okay, that slab is lightweight concrete. I think the deck that supports the slab is 1.2 millimeters thick, and the steel is procured from a basic oxygen furnace, and I've arrived at a carbon value of 150 kilograms per meter squared of CO2. But the reality might be, if you go to the next click through, it might be a normal weight slab, which has considerably less carbon. The deck might only be, if you click, 1 millimeter thick, and the steel might be produced by an electric arc furnace. And that would actually drop the carbon of that floor plate down to something closer to 98 kilograms of CO2 per meter squared, which is almost a 50 or 33% difference depending on how you cut it. If you go to the next slide, similarly, you might model beams and slabs for a concrete structure in BIM. They get joined in BIM, but ultimately the quantities we're going to extract either assumes on the left that the beam is the segment of concrete just under the slab, or on the right where the beam takes priority and it displaces the slab quantities. If you click, so on the left you would get sort of 0.45 meters cubed of slab, 0.15 meters cubed of beam, and you might assign reinforcing rates that are fairly low in that perspective. If you jump to if you click again, the contrast would be a slab that has less volume and a beam that has more volume. And you might also say that the assumptions were wrong on the reinforcing, and this is actually a heavily reinforced slab and beam. Again, you're yielding results that are about 10 to 15% different when we're ultimately, for LEED or other requirements, seeking 10% reductions. So the ability to introduce error here is high unless we're really explicit about what we're counting and how. You go to the next slide. And so within the deck, we've sort of highlighted ways to document your assumptions as you move through based on all of the different things that we've noted in all the previous presenters.
So I'm going to bring us home. You've heard, and from all of these folks about what we've learned, and we've compiled recommendations and checklists shared today for the industry to reduce variation in embodied carbon processes as they relate to BIM. So now we're going to go back and we're going to compare to our first round of work and see if we can put our own best practices to purpose and see the results. So I shared this image before. This group applied these guidelines that we presented today to reassess the work. And as a reminder, we're looking at the high carbon impact scope of structural systems, and we deployed these best practices. Now, when we did this, the group demonstrated, if you could click please, a variation from 34% to 19.6%. So we've cut this down quite a bit. On the next slide, we'll compare the results from before and after. In aggregate, we did see a 43% reduction compared to the first phase. This shows that when we are intentional about BIM processes and our workflows, we can directly reduce the uncertainty associated with BIM and inherent in an embodied carbon assessment. But we did not get it to zero. And it's important to note that that's because there are still many other factors at play. We could not solve everything at once. Technical guidance alone, which we're addressing here for BIM workflows, cannot address all the variation potential, and we just want to acknowledge that additional alignment is still needed through continuous engagement by technology providers, policymakers, industry groups, and organizations that establish embodied carbon reporting frameworks. So compared to the proof of concept, the Phase 2 results that we shared today demonstrate greater alignment in the quantity estimation for, in this case, concrete across the group. However, the selection of embodied carbon factors, which were outside the scope of this alignment, are still a factor. Everyone selected their own carbon factor, which is a contribution to the variation in the overall results. Now, although we were able to demonstrate a reduction in variance, we do want to reiterate that the focus of this work was on the process of extracting quantities from BIM. So this graphic here, it maps the carbon factors, the volumes, go back please, and the resultant, embodied carbon of concrete for the RICS category 2.2.1 around structural slabs. And again, it was a high impact category. And you'll also note that while we see a close range of BIM volumes, there are still some discrepancies due to some specific workflows. On the next slide, I'm sorry, you were on the right slide before. Just to regroup, this is a triple click into carbon factors and volumes. Sorry for the misalignment there. To bring us home, let me walk you through a summary of takeaways and guidance from each of the 6 sections that were presented today. Number 1, identify key criteria of the assessment, including LCA scope, spatial scope, click please, purpose, and the reporting framework. Thank you. Number 2, set up a model based on the criteria you set up in step 1. Specifically, click please, the geometry and the associated metadata. Step 3, establish a model element table with clear data responsibilities assigned to project stakeholders. Step 4, address high impact, commonly non-modeled elements such as steel rebar, metal deck, and wall studs. Number 5, address the common pitfalls, some of which we introduced today, like mapping BIM to a reporting framework, extracting the data, or mapping carbon factors. And number 6, provide assumptions relative to the quantities, the non-modeled elements, and the carbon factor data so that everyone can know. These combined steps are crucial for communicating results transparently based on assumptions and inputs to everyone and all the stakeholders on a project. So scan this QR code because here is where you can read about the work and the much more detailed guidelines we've shared today. This report is called A Guide to Alignment in the Built Environment, Step-by-Step Recommendations for Consistent and Transparent Embodied Carbon Assessments through Building Information Modeling Workflow Optimization. It's no small feat to get this expert group of designers and engineers to put their carbon expertise together and to spend time to really get down to the root causes of carbon assessment variation. As you can see, we had so many Zoom meetings and a hearty dose of transparency and effort, but collaboration was the secret sauce, preparing these insightful learnings and insights. And just remember, this is just a slice of the many stakeholders who truly look at whole life carbon assessment. We were really zeroing in on a very specific process so that we could think about its overall magnitude. So as I introduced at the beginning, we will be initiating a phase 3 to uncover processes and insights with additional stakeholders to widen the aperture in how we address this problem. Many thanks to the practitioners and those here today. I'm going to hand this off to Rama and just re-emphasize the fact that this radical collaboration, as well as clear policies and reporting frameworks, together with technology, are critical to support these workflows and narrow the gap for best practices in BIM.
Thank you so much, Marta. I know we're at the top of the hour, but I think we'd love to take a couple more minutes to just go through some questions for the cohort. Thank you again for all being here today to present from around the world. So I'm going to start off the Q&A and then we'll look obviously to the chat. Please, anyone in the audience, feel free to ask a question. And so I'm going to actually open it up to Sandra from Arcadis and say kind of, have you applied any of the learnings from the research that you've done? I think everybody also can come off camera. Come onto camera, come off camera. Have you applied any of the learnings from this collaboration to work in your firm?
Thanks, Rama. Well, for companies like Arcadis, we're so big, so as a firm, so even having internal alignment is a really big challenge. So these conversations we've been having with our cohort here has given us like actual tools to have these conversations internally and start reviewing our processes and see like how we're actually doing it from region to region, from service to service, so we can have a proper alignment internally and then continue steering that with the rest of the cohort. So we all eventually end up on a one direction at one point.
Great. Paul, did you want to add anything from your point of view?
On the same topic, so absolutely in Ramboll, we've been using both phases of this cohort to really illustrate the potential pitfalls of inconsistency and what we've got to do as a business to try and address that. And it is a very big challenge globally because there's so many different methodologies, but I do think that there's some really important practical steps that we can all take, regardless of the tools or the methodology. And we are now trying to build best practice guides around this internally to do that. So absolutely, it's been a really useful catalyst for that process. But I also recognize there's still a long way to go.
Excellent. And actually, I want to ask you, Marta, from Autodesk point of view, were there key learnings from this collaboration internally at our company?
Yeah, well, internally and externally, because we know that digital tools are a prerequisite for any carbon assessment. There's also a lot of software tools that do this work. We happen to show just, again, a thin slice of what's possible. And when we think about the ecosystem of all these different tools, it's really unclear whether they're comparable. What if the results are apples to oranges and good or bad or best? So this effort was really enlightening and validating that digital workflows can vary, and that's going to affect the results. I'm really happy that this work shines a light on this reality of software and technology today. That said, digital tools are constantly improving, and there's huge upside for the future. I think for now, it's really important that this is being shared at places like COP and is understood by policymakers and industry groups and practitioners, because we have to work together to close this gap and work towards alignment so we can really drive those decarbonization goals. This is just the beginning.
Excellent. I'm going to keep asking questions until we get some good ones from the audience. So please feel free to chime in with a question. So I'm going to over to you, Chris at Foster's. Was there anything like what did you find most surprising in the most surprising finding through the work?
Yeah, well, I suppose as the numbers demonstrate, there's still quite a variance in the calculated results through the different the same methodologies in different companies and how they're approaching it. And even for structure, which you might take as a kind of the one area of a building where there's probably fewer choice in elements than there is elsewhere. So there is still quite a big variance to understand, but I don't think that's necessarily all a downside. It's given us confidence and transparency, and the absolute number isn't necessarily the the North Star here. What you want is consistency in the approach, and to know that you're getting usable and repeatable good directional results that are telling you where to go next, and that other people would agree with you if you shared that information. So I think those were the kind of the key elements in terms of the surprise. But then the reaction to the surprise is, okay, we now have known unknowns rather than unknown unknowns, which I think is a pretty good place to be.
Excellent. AECOM, Laura, or Javier, do you have any questions? Do you want to? Oh, Jordan, also, if you wanted to respond, feel free to chime in. But come on,
I'll just piggyback on what Chris just said. I think when we're doing a carbon assessment, it's largely, there's a couple different purposes of why we could be doing it. On a single project, we can track the progress of how we've reduced carbon over time, and internal consistency can yield that very quickly. You're as Chris mentioned, you have one approach, and you can sort of consistently be off or on the right number, so to speak, as long as you're doing things the same way. And you're easily able to track carbon sort of on the same basis. It's when we want to expand to like a portfolio or global level of having benchmarks, of having standards, of knowing, building A versus building B's carbon intensity, that we really have to institute more rigid sort of constraints as to how these things are done. But I wouldn't say, I would certainly say don't let the inconsistencies that sort of are highlighted by the approach prevent people from doing it directly on projects right now.
Thanks, Jordan. We have a question from the audience. It says, thank you for this amazing collaboration. This is open for anybody on the panel to answer. And the shared experience, I have one question. How can the use of BIM models during the early design stages improve coordination, decision-making, and overall efficiency in the development of MEP systems? And what challenges still limit its full potential at this stage? Is there anyone who wants to take on that question?
Ram, I can go. I can just maybe say that I think there is a big challenge with the MEP systems right now. Especially one of the major challenges is that the lack of information in the industry, lack of environmental product declarations to actually kind of report how the systems and what the embodied carbon of the systems is. So based on that, it's very hard to build on a proper carbon assessment for MEP without having that kind of information. Definitely, I think the industry is building now on that, and the software also will help towards achieving a proper carbon assessment with the MEP. But until we have enough information with TPDs, it's very hard to actually account for that carbon.
Great. So I think I'm going to call on Eric to take us home. So of the six topics we discussed, and amongst the cohort, what did you think was the hardest thing for us all to come to alignment on? Like this was the direction we were going to move forward.
Oh, gosh.
Put you on the spot.
I think, the biggest thing that I struggle with in this effort is that we're trying to use the BIM, the model, to extract this data. And there's a lot of things, that this question about MEP systems is spot on. In the early stages of a project, there's often not very much modeled for the MEP systems. And so what you're really able to get out of a BIM model is the quantity of something. And if you don't have anything in there, then it falls back onto like you have to build up all of these assumptions and just doing that consistently across the industry and across different companies and teams is super challenging. So I think that's the big wild card here is that we have we're not in a way we can't rely on the model because the model is not sufficient, certainly at that stage. And so having transparency of our assumptions, super important.
I lied. I feel like 10 minutes over will be the limit. So just one last question from the audience, because I want to make sure that we address them. So it says here, I don't know if everybody read it, from Francesco, could there be a risk that even doing all that's needed, the final result might be affected by the carbon factor of the supplies and accessories introduced during the final and detailed design phase? Anyone want to take that? And then I think this will definitely be the last question, and then we can wrap it up.
I can come in on that. Just to say, it's a very good point. And of course, we've been talking about trying to look at the materials volumes separately from the carbon. And of course, the carbon is a whole separate discussion, but I think that this work is super important because regardless of your carbon factor, it's important to have an efficient design. So what we're talking about here is using this information, getting consistent takeoff that allows you to do some work on efficiency and work out making sure you've got an efficient building, an efficient design. The carbon factors then come in afterwards. And so, yes, they may change things, but that doesn't mean that the work you do to get the consistent takeoff is invalid. It's still very important.
Excellent. Well, thank you to the audience for sticking with us through this presentation. I hope you found it enlightening, valuable, and applicable to the work that you're doing, whether you're a practitioner or in policy. And for those of you who are obviously to the working group and the cohort, a massive thank you for 2 years of incredible work, unbelievable transparency, and great collaboration. So hopefully we're giving this back to the industry and that these guidelines will help people in their day-to-day work. So thank you and have a wonderful day. Thanks all.
Thank you.
Thank you very much.
Thank you, everyone. Thank you, everyone.
Thank you.